So in this section, we're going to look at the derivative of a function and look at the derivative as a function itself. So in the last few sections, we've looked at the difference quotient definition to calculate the slope of a tangent line at any one point. And what that would give us is a numerical value for the slope at that particular place. Well, what we want to do now is actually assign an x to what we had as an a, and as a result, get what we refer to as the derivative function, right? So this would be a function that would allow me to calculate the slope at various points. We call it derivative because it has it's been derived from the function itself. And the other fact we want to be careful with is that the domain of the derivative is the set of all the x's where f prime exists, and maybe smaller than the domain of the function f itself, right? So later on in this section, we're going to talk about differentiability and finding out which value of the domain of the function can be used for the f prime, and where does the f prime actually exist, right? So it's a limit, so it may not exist because the left and the right limits don't match, or because some value would make the resulting function undefined. So we'll look at those coming up. We also want to take a look and see how the graph of the derivative relates to the graph of the function itself. So suppose this is a function f of x, and we are interested in looking at see how the graph of f prime of x would look like. So remember, the f prime of x gives me a function that lets me calculate the slope of the tangent line at various points. So if I kind of look at the tangents to this graph at different places, so we'll notice that to start with, this graph has positive slopes. It's kind of the slope keeps getting smaller, even though it's positive, keeps getting smaller and smaller until it reaches 0 up here, and then the graph starts going down. So I'm going to have negative slope for the tangent line. Again, down here I have a slope of 0. Then the slope keeps increasing, and then around here it starts decreasing again, it starts getting flatter and flatter. So if I want to kind of now look and see what the derivatives graph would look like, it would start being positive and kind of larger, and it's going to start getting smaller. So it would start up here and start getting smaller, and then it will become 0 right here. So the graph's going to come here and become 0 because right up at that point I have a horizontal tangent, so the slope would be 0, and then it will become negative because, as you notice, the slope of the tangent is negative, so we'll go down, and then it will start coming back up because the slope starts getting bigger until it hits 0 again right here, right? So this line has this tangent line is horizontal, so the slope of the tangent right here would be horizontal, and so on. So if we kind of look at what that graph would look like, so this is the graph of f prime of x. This is a rough sketch of it. Right, so it starts as a positive value. It keeps getting smaller because the slope gets smaller. Right here it's 0. Then it becomes negative, and right there, since I have a horizontal tangent, the slope becomes the derivative becomes a 0 again. Right, and then it gets bigger, and at some point it changes and it keeps getting smaller. It almost becomes a 0. But this function is not going to become horizontal. It's just going to continue growing, but the slope is pretty small, so the slope's going to get small, right? So just for us to get an idea of how the slope of a how the graph of a derivative represents the slope of a function at various points and how those two graphs relate to each other. All right, so let's look at an example numerically as a function, and then maybe take a look at a graph of this. So if I have a function 2x squared plus 5x minus 4, I want to find the derivative function for f of x. So we'll start with our difference quotient definition for the derivative function. Replace all our x's in our function with x plus h. So this is f of x plus h minus f of x over h. Next thing I'm going to do is take x plus h quantity and square it by expanding it. Becomes 2x, it becomes x squared plus 2xh plus h squared. So that's x plus h quantity squared. Then distribute everything in. For the second parentheses, we want to make sure we distribute the negative into that parentheses. That's one of the common mistakes that happen quite often, is we forget to distribute negatives. So this is what we get. So that's the 2 being distributed, the 5 was distributed, and the negative was distributed to the second parentheses. And then we can cancel some of these terms. The 2x squareds cancel, the 5x and the negative 5x cancel, and the 4 and the negative 4 cancel each other. So we're left with 3 terms, 4xh, 2h squared, and 5h. They all have an h in common. We're going to factor that h out. And then that lets me cancel the h on the top with h on the bottom. H becomes very, very close to 0, but it's not 0 itself. So I'm allowed to cancel, right? So, and then what I'm left with is just 4x plus 2h plus 5. As h goes to 0, 4x and 5 remain the same, but 2h becomes 2 times 0. So we just have 4x plus 5 as our final answer. So that's the derivative function for 2x squared plus 5x minus 4. And if I now go back and look at the graph of these functions, this is what the graph of our function we started with looks like. It was a parabola, 2x squared plus 5x minus 4. And if you look at this graph, this has a negative slope. It is going down. It keeps going down. It has a negative slope, negative slope, negative slope, until right here at negative 1, it becomes a 0. So here I have a horizontal tangent, so the derivative is 0, the slope is 0, and then it becomes positive and it keeps growing. And that's somewhat consistent with the value or the function we got for the derivative, which was 4x plus 5. And this is what that graph of 4x plus 5 would look like. It is negative to start with, right? Because this graph was had a negative slope. So our graph is negative. And then once we hit negative 1, the graph becomes 0, right? The slope becomes 0. So our graph has a y value 0, and then it keeps increasing. And then it becomes positive because the slope after that point keeps increasing. Okay, so let's maybe consider one more example here. Here we want to find the derivative function for square root of x plus 5. So once again, we'll start with the definition, the difference quotient definition for the derivative function. Replace the x in our function with x plus h. So we have square root of x plus h plus 5 minus f of x, square root of x plus 5. Now, next thing we need to do is kind of simplify this by multiplying it with its conjugate. So multiplying by the conjugate allows us to rationalize the square root, so get this numerator rationalize, get rid of the square roots in the numerator, and simplify it. So remember, you multiply by the conjugate. You got to multiply both on the top and on the bottom, right? So the conjugate, again, just changes this subtraction to an addition, and then we got to multiply it on the bottom also. So what that's going to let us do is in the numerator, when I multiply this binomial with its conjugate, the square roots go away, right? So if I multiply a minus b with a plus b, you get a squared minus b squared, so the square roots go away. And then I will again distribute the negative into the second parentheses and simplify what we have. So once the negative is distributed, that lets me cancel the two x's and cancel the two 5's and only have an h on the top, right? So the denominator, I haven't distributed because what I would like to do in most of these difference quotients, whenever possible, is cancel the h that's on the bottom with the h that would be on the top. And get an expression that doesn't have that zero term in the denominator anymore and in the numerator. So the h's cancel again, and what I'm left with is the limit as h goes to 0, 1 over the conjugate of what we started with, square root of x plus h plus 5 plus square root of x plus 5. And then I can start taking the limit as h goes to 0. So again, this term, the square root of x plus 5 term, is not affected. The first square root, though, the h becomes 0, so you just get x plus 5, or x plus 0 plus 5. Once we take the limit, that h becomes very, very close to 0. And as a result, I have 1 over square root of x plus 5 plus another square root of x plus 5, and I can combine those. Square root of x plus 5 plus square root of x plus 5 gives me 2 square root of x plus 5 in the denominator of this fraction. Right? So next thing we're going to look at are just other notations for derivatives that have been used depending on the context of how we're going to use the derivative. And there are many, many applications of derivatives. And depending on the number of variables in the problem or the application, different notations tend to be more convenient. So some of the notations we have now used so far, we've used f prime of x for the derivative. We have used y prime for it. We also have a derivative notation of dy over dx. It's used kind of to show what our variables are that we're taking the derivative of. And that, again, comes in handy if I have more than 2 variables in the problem. So it tells me what my dependent variable is, what my independent variable is. And it kind of has the same look as what the definition of a slope would be, change in y over change in x, and that's not by coincidence, right? So if we take the change in y over change in x and let those changes become smaller and smaller, and we get what we refer to as the Leibniz notation for derivative, dy over dx. And or df over dx if we have used the function notation. And there are, again, other ways this can be written: d over dx of some function f of x. And you may see this capital D f of x that's used as a differential operator. Indicates the operation of taking the derivative, and we may also use that with a subscript if there are multiple variables and they're telling us what we took the derivative with respect to, right? What was our independent variable as we took the derivative? And again, just for the sake of consistency, We want to also make sure we know how to evaluate these derivatives. So if I have an f prime of a, that would mean I evaluate my derivative at a, or I found the slope at one particular point. In the Leibniz notation, this is how it's usually indicated with a dy dx, a vertical line, and a subscript that says what the value of x is. So x equals a. Usually it's a line. Occasionally you may see a half bracket on the right side. So now that we've looked at different definitions and notations, next thing we want to define, what does it mean for a function to be differentiable? Right. So by definition, we say a function is differentiable at a value a if f prime of a exists. Right. So I can take find the derivative function and evaluate it at a, and that value does exist, right? So the limit from the left and the right, if I was going to take the limit, would have given me the same answer, and I can actually plug in a into the derivative function. We say it's differentiable at an open interval from a to b, or a to infinity, or negative infinity to a, or negative infinity to infinity. So on some open interval, whichever form we have, if it is differentiable at every number in that interval, right? So then we say it's differentiable on the entire interval. Okay, so now that we've talked about differentiability, next question that comes up is, are all functions differentiable? Can I find a derivative function? And when, if not, are they not differentiable? So our first theorem tells us that if f is differentiable at a, then f is continuous at a. Right, so we've defined what it means for a function to be continuous before. Its left limit, right limit, and the value of the function at a all match. This theorem says if it is differentiable, so then it has to be continuous at a. Now, you got to be careful. The converse of this theorem is false, right? So just because a function's continuous doesn't mean it is differentiable. A good counterexample would be absolute value of x. It is continuous at 0, right? It's a V shape. But if I look at the limit from the left at 0, the slope would be -1. It's a line coming down. At the other side, the slope is +1. So the limit as h goes to 0 of f of x plus h minus f of x over h would not exist. Therefore, the derivative doesn't exist, even though our function itself is continuous. So next thing we'll kind of want to talk about are the higher derivative notations of derivatives. Now that we know how to find a derivative function, we can also find the derivative of the derivative function. So find out how fast our rate of change itself is increasing. So in a physical sense, the derivative would give me the velocity, how fast something is increasing. If I take a derivative of that, I would find the acceleration, how fast the velocity itself would be increasing. So notationally, we use 2 primes. We call this a double prime. So f double prime of x, or y double prime of x if we're using y as our dependent variable. We could write it as d over dx of dy dx. That means the first time we took a derivative of y with respect to x, I'm taking the derivative of it again with respect to x second time, and that also can be written as a d squared y over dx squared, right? So if you kind of want to look at it, the squares here aren't really exponents. They're just notation. This means we took the derivative twice of y, and this tells me the derivative both times was with respect to x. And as we move on in the next course, we talk about multivariable calculus, and there we may have an equation with more than two variables in it, and we may want to find the derivative with respect to different variables for our second derivative. And again, if you're going to go on, we may look at the triple prime of x, and notationally, that means I'm taking the derivative of the second derivative, and this is what we would write it in Leibniz notation. D cubed the y derivative was taken 3 times over dx cubed, all 3 times with respect to x. And again, we could continue with some functions. We can take the derivative over and over and over again. Now, putting little dashes on primes on top could become a little messy. So at some point, we are going to switch after 3 usually. We switch to parentheses with a number up there. So if it was the 4th derivative, it would be f to the 4th, and the 4 would be in the parentheses just to distinguish between it being an exponent versus it being a derivative. So you would have y to the 4th with a parentheses around the 4, rather than y to the 4th, which would mean an exponent of 4. But the Leibniz notation should have less confusion, so we don't need the parentheses here because there's no confusion. Okay, and now that we've talked about this, the derivatives in general, just to summarize what the derivative tells us. A derivative tells us if it's positive. If my derivative function is positive on an interval, then my function itself is increasing, because remember, the derivative gives me the slope of a function. And if it is a negative, then my function is decreasing. And in the next section, we're going to talk about other faster way to find derivatives of various functions.